share my screen.
Okay, sure. No problem. I
I'm
I think
trying
your
to share.
screen. Oh, okay.
Hmm?
I can actually see your presentation slides. Yep.
Now you can see.
Yeah, I can see your slides.
Okay.
Prof. Yeah.
So thank you very much for inviting me to your Malaysia's chapter of IEEE. And today I'm happy to give you a basic idea of evolutionary multi-objective optimization. Oh, what's up? Sorry, something happened. How can I go back to? Oh, okay. Okay. Okay, thank you very much. This is the first time for me to use this system. And today's talk is on introduction to evolutionary multi-objective optimization. And first, I'd like to explain my main research field. When I was young, I was under Professor Hideo Tanaka's lab in the industrial engineering department in Japan. And Professor Tanaka's main research topic was fuzzy mathematical programming and fuzzy regression and fuzzy classification. That is what fuzzy data analysis. So I worked on this topic and I tried to apply neural networks for fuzzy data analysis. And also I tried to use evolutionary multi-objective optimization for fuzzy classification. And also I tried to use evolutionary multi-objective optimization for scheduling. This part is because I was with the industrial engineering department. Then, fortunately, I promoted to professor and I had my own research group. Then, industrial engineering department was not so popular. Thus, this department was destructured and disappeared. And half of members in I department were moved to computer science, and the other half moved to electrical engineering. I moved to computer science department, and then I worked on fuzzy classification, evolutionary multi-objective optimization for fuzzy classification, evolutionary multi-objective optimization, and evolutionary games. Then 5 years ago, I moved to China, and currently I'm in the computer science engineering department. And my current topic is evolutionary multi-objective optimization. And today's topic is on evolutionary multi-objective optimization, GSPAT. And this is today's plan. First, I'd like to explain evolutionary computation, basic idea of evolutionary computation, then multi-objective optimization. After that, this is the main part, evolutionary multi-objective optimization. Then I'd like to explain some current hot topics in the MO field. And finally, I'd like to give some useful information on MO research. This slide shows a basic search mechanism, local search. Local search is the most simple search mechanism. We use an initial solution, we usually randomly select the initial solution. And local search will find this local solution. If we start with different initial solution, we will find different local solution. One simple extension is iterated local search, starting from initial solution to go to local solution. Then we move to a different initial solution, then go to local solution, and then move to different initial solution. Then try to find a local solution and go to another initial solution. Simply iterate local solution. All of these mechanisms are point-based search. We always use a single point to search good solution. A little bit intelligent search is a taboo search. As in local search, we start from an initial solution, then go to local solution. Then using taboo list, we can climb up this hill and then go to another local solution. Then again, escape from local solution and go to another local solution. In this manner, we can escape from local solution in taboo search. Simulated annealing uses the concept of temperature. In initial stage, temperature is high. This means that solution has a high activity level, so solution can move almost everywhere. Then temperature is gradually decreased. And then solution's activity level becomes lower and lower. Finally, solution converges to this solution. This is the basic idea of simulated annealing. Again, this search mechanism are point-based search. That is, we always use only a single point to search for good solution. On the contrary, evolutionary computation, for example, genetic algorithms, they have population-based search algorithm. That is, multi-point search algorithm. We usually randomly generate many initial solutions. Then each solution is evaluated and focus on better solutions. And using these better solutions, we create new solutions. And then those solutions are evaluated and again focus on better solutions. Then create new solutions. In this manner, we can find good solutions. This is the basic idea of evolutionary computation. The main characteristic feature is population-based search. And we usually use two mechanisms to generate new solutions. One is mutation. Mutation is similar to local search. Randomly generate a neighboring solution by slightly changing a part of the current solution. Then new solutions are generated. The other is crossover. Crossover usually use two parents. From two solutions, we generate a new solution. From two solutions, we generate a new solution. And using this figure, I'd like to explain evolutionary computation again. First, we randomly generate initial solutions. A population of individuals is randomly generated. Then each individual is evaluated in the environment. We have environment, and each solution is evaluated under this environment. Then good solutions are survived. Good solutions survive probabilistically. We choose some good solutions. Then from those good solutions, we generate new solutions. New individuals are generated from the good individuals. Then again, these solutions are evaluated and we select only good solutions. And from good solutions, we generate new solutions. So step 2 and 3 and 4, these steps are iterated many times. Then after many generations, we may have good solutions. Here we have, finally, we may have good solutions. This is the basic idea of evolutionary computation. And we have at least two advantages in evolutionary computation. One is population-based search can escape from local solutions. Since we have many solutions and we use crossover, then we can create new solutions outside the local region. So population-based search can escape from local solution. This is one advantage. And another advantage is any evaluation mechanism can be used. In order to evaluate each solution, we can use any evaluation mechanism, not necessarily by a mathematical formulation. We can, for example, we can use evaluation by human users. You can intuitively choose, oh, this is nice, this is nice. Well, we can use computer simulation for each solution. Each solution is used, as, for example, as a parameter in computer simulation. Well, we can use multiple objective functions. Today's topic is this part, multiple objective function. Each solution has multiple objective functions. And this slide shows the categorization of optimization problems. Depending on the number of objectives, optimization problem can be categorized into single objective problem and multi-objective problem. Single objective problem has only a single objective. Here, maximization of fx, we have only a single objective. And multi-objective problem is characterized by multiple objectives. Here we have F1, F2, Fm, M objectives. So if we have only a single objective, this is a single objective problem. If we have two objectives, this is a multi-objective problem. If we have 3 objectives, 4 objectives, 5 objectives, and 1 objective, all of them are multi-objective problems. And this slide shows the popularity of multi-objective optimization research using Scopus database. We created this figure, and the height of each bar shows the number of papers published in each year with multi-objective or multi-objective in the paper title. We only count the number of papers with multi-objective in the paper title. And last year, we have about 5,000 papers. Those papers have multi-objective in the paper title. So this figure clearly shows the increase, stable growth in the number of published papers on multi-objective optimization. This slide also shows the popularity of multi-objective optimization research. These 5 papers are outstanding paper award winners in the last 5 years. You can find some very hot topics. Deep learning is the most popular research topic in the AI field currently, and multitasking is also a popular topic. And then the other 3 papers, among 3 papers are on multi-objective optimization. Many objective optimization, many objective algorithm, and multi-objective optimization. So this slide also shows the popularity of multi-objective optimization research in the field of evolutionary computation. And why multi-objective optimization is so popular? The reason is very clear. Almost all real-world programs have multiple objectives. For example, let's just assume that we are trying to design an intelligent system. For example, pattern classification system. The main objective is clear, maximization of the performance. For example, error minimization. This is the main objective. However, we also have several other objectives. For example, cost minimization. We need some cost to design or develop a classifier. So we want to minimize the cost. And design classifier needs some energy, electricity. So we want to minimize the energy consumption. Also, we want to try to develop a simple system. So complexity minimization. Simple system is good because we can easily understand, we can easily modify, we can easily improve. And this slide shows the idea of complexity minimization and error minimization in the design of neural network structure. Our main goal is to minimize the error of neural networks. And our problem is to find a good structure of neural networks. In order to minimize the error, complexity will increase. And in order to minimize the complexity, error will increase. If we use very simple neural network, it's not so easy to have a high accuracy. So there is a clear trade-off relation between complexity minimization and the error minimization. This trade-off relation is the most important concept in multi-objective optimization. even when we use the same structure, we still have trade-off relation between cost and error. For example, cost can be evaluated as computation time, training time. By increasing the computation time, by increasing the training time, we can improve the error. However, we want to have a neural network after a very short training time, if possible. So cost minimization, computation time minimization is one objective, but if we use very short computation time, error will be large. And in order to decrease the error, computation time will be increased. So we have clear trade-off relation between error and cost. And cost can be dataset size. By using a large dataset, we will have a nice, highly accurate neural network. If the dataset size is very small, error may be large. However, small dataset is good from the viewpoint of cost. In order to obtain large dataset, we need cost and time. So we want to design neural network using a small dataset. So there is a clear trade-off between error and cost with respect to the dataset size. And we also have a trade-off between two types of errors. One is on one dataset and the other is on another dataset. We want to have a neural network for these two datasets. We want to have a single neural network for these two different datasets. And in order to minimize the error for dataset 2, then the error on dataset 1 will increase. In order to minimize the error on dataset 1, the error on dataset 2 will be increased. So again, there is a trade-off relation. Two datasets can be considered as patterns in each class. So this axis can be the error on class 1 pattern, and this axis can be the error on class 2 patterns. Then there is a trade-off between class 1 pattern errors and class 2 pattern errors. And then we can also consider two different types of errors for different users. If we carefully tune the parameters for user 2 in order to minimize the error for user 2, that neural network will be specialized to user 2. Then error for user 1 will be increased. So there is a trade-off between errors for user 2 and errors for user 1. This is one simulation result for fuzzy classifier design. We try to minimize the error, training data error and test data error. And the other objective is number of fuzzy rules. We want to create fuzzy classifier system using small number of fuzzy rules. So the other objective is to minimization of the number of fuzzy rules. And we can see this clear trade-off relation between the number of fuzzy rules and the error rate on training data. By increasing the number of fuzzy rules, we can decrease the error rate on training data. Of course, we have different results on test data because there is overfitting to training data here. So the test data result is different from clear trade-off. But for training data result, we can observe clear trade-off relation between the complexity, that is the number of fuzzy rules, and the accuracy, that is the error on training data. But some objectives are related. In the case of complexity and error, we have clear conflicting relations between two objectives. However, in some objectives are related and partially conflicting. I worked on the maximization of interval objective function about 30 years ago. Our goal is to maximize an interval objective function. In order to maximize an interval objective function, we considered 4 different objectives. First one is maximization of the lower limit. That is the worst case maximization. And second one is maximization of the upper limit. This is the best case maximization. And third one is the center, average case maximization. And then last one is the minimization of the width. That is the uncertainty minimization. All of them are clearly related to each other, but partially conflicting. Another example is scheduling program. In scheduling program, we usually use maximum and delay. So for example, the minimization of the maximum is the one objective, and minimization of the maximum delay is another objective. And minimization of the total delay is also another objective. Those objectives are related, clearly related, but also partially conflicting. This slide shows the simplest formulation of multi-objective optimization problem. 2 objective maximization problem. We have only 2 objectives, F1 and F2. Both are to be maximized. And this is the objective space. This axis is to maximize F1x, and this axis is to maximize F2x. And the solutions of this problem are point in this objective space. If we have these 2 solutions, B and A, it is clear that A is better than B, because this is a maximization problem, and A is better than B for F1, and A is better than B for F2. Thus, we can say that A is better than B. In the field of multi-objective optimization, in this situation, we say that A dominates B, and B is dominated by A. However, if we have solution C here, C is better than B. It is clear that C is better than B. But between A and C, we cannot say which is better. This is because C is better than A for F1, but A is better than C for F2. So we cannot say which is better between A and C. In this case, we say that A and C are non-dominated with each other. These 2 solutions are non-dominated solutions. And using solution A, we can divide this objective space into 4 regions. These pink regions, the beta regions. Solution in these regions are better than solution A. A quarter of the space is better than solution A. And the opposite side, this side, solution in this region are dominated by solution A. So this is a worse region than A. And these are 2 regions. These 2 regions are typical in multi-objective optimization. These regions are non-dominated regions. Solutions in these 2 regions are non-dominated with solution A. So we cannot say which is better between A and any solution in these 2 regions. Now I can show the most important concept, Pareto dominance relation. We can mathematically show this concept. Let's assume that we have M objective maximization problem. For this problem, the definition of dominance is this one. X is dominated by Y. This is defined by this mathematical formulation. This mathematical formulation means that for all objectives, Y is better than X or equal, and at least one objective, Y is better. This is because this relation includes the always same. For all objectives, X and Y are the same. In order to exclude the special case, we need this additional condition. For at least one objective, Y is better than X. This definition is exactly the same as this definition. The first part is the same, and second part is these 2 solutions are different in the objective space. And this is a basic concept of multi-objective optimization. And for minimization, the idea is exactly the same. Simply change the direction of inequality relations. Now we can define Pareto optimal solution, the optimality of solution in multi-objective optimization. A Pareto optimal solution is a solution that is not dominated by any other solutions. This is the objective space. In objective space, G's pink point are, not dominated by any other solution. So all of G's pink point are Pareto optimal solutions. For example, this one, no solution in this region. So this solution is not dominated by any other solutions. However, this white point, this one, is dominated by some other solutions. So this white point is not the Pareto optimal solution. All of these white point are dominated solution, not Pareto optimal. All of these pink point are Pareto optimal solutions in objective space. And in decision space, we have some solutions related to each point in the objective space. And we cannot say which solution is the best solution among these Pareto optimal solutions. All of Pareto optimal solutions are optimal in multi-objective optimization. We cannot say which is the best. And the set of all Pareto optimal solutions, a set of all Pareto optimal solutions in the decision space. This set is the Pareto set or Pareto optimal solution set. And in the objective space, these solutions, the set of all of these Pareto optimal solutions are Pareto front. These are simply the names, different name. We use a different name in different space. In decision space, we use Pareto set or Pareto optimal solution set. In the objective space, we call them Pareto front. This is a front. We can not go beyond this front. This is a boundary in the objective space. And the best trade-off is the Pareto front. Now I'd like to move to evolutionary multi-objective optimization. The goal of evolutionary multi-objective optimization is to find all Pareto optimal solutions. This is a very simple explanation. The goal of evolutionary multi-objective optimization is to find all Pareto optimal solutions when the number of Pareto optimal solutions is small. For example, if the number of Pareto optimal solutions is 100, the goal is to find all of those 100 solutions. However, in some program, the number of Pareto optimal solutions is huge or infinite in the case of continuous multi-objective optimization program. In this case, the goal of evolutionary multi-objective optimization is to find a solution set which will approximate the entire Pareto front. So if we have infinitely large number of solutions on this Pareto front, our goal is to find a solution set to approximate this Pareto front. Traditionally, we have two approaches to multi-objective optimization. One is evolutionary multi-objective optimization. The other is MCDM, multi-criteria decision-making approach. First, I'd like to briefly explain the multi-objective approach. Multi-objective approach is characterized by the use of additional information after optimization. In multi-objective optimization approach, first, a number of Pareto optimal solutions are found. These solutions are found and presented to decision maker. These solutions are presented to the decision maker. Then, a final solution, a single final solution is selected by the decision maker. The first step is to find these solutions and present these solutions to the decision maker. Then, second step, decision maker will choose a single final solution. This is a MO approach. So in the first step, MO algorithm try to find all of these solutions. The first step is search for non-dominated solutions along the Pareto front. And the second step is by the decision maker. a single solution from the obtained solutions is selected by a decision maker. And usually, evolutionary multi-objective optimization focus only on this part, step 1. The second part is the decision-making problem. So the optimization problem is the first part. The other approach, this is a more traditional one, use of additional information before optimization. Before optimization, we use some information. In this approach, first, multiple objectives are combined into a single objective function using additional information from the decision maker. Then, objective function is optimized to find a single final solution. But the simplest approach is weighted sum. Here, two objectives are combined using two weights into a single objective. Then this single objective is optimized. The first step in multi-criteria decision-making MCDM approach is to create a single objective function using multiple objectives. That's the formulation of a single objective optimization problem using multiple objectives. Then this single objective optimization single objective function is optimized. The second step is optimization. First step is program reformulation. And if we use genetic algorithms in the second step, we will find a single solution here. This slide shows a comparison between these two approaches to objective evolutionary optimization and weighted sum approach. In M approach, a large number of solutions are obtained along the palette front. In MCDM approach, especially in weighted sum, we have a solution here using the weighted sum approach. Only a single base solution with respect to the weighted sum is obtained. And one advantage of M approach is that the palette front is shown to the decision maker as a result of a single run of an M algorithm. So all of these solutions are obtained. So decision maker can understand the shape of the palette front. However, in the weighted sum approach, only a single point is shown to the decision maker. This is your solution. Then decision maker simply accepts this one. And in some cases, not always, the M solutions have the better convergence than the single objective solution. These two results are obtained after the same computation load, after 2000 generation updates. Using M approach, we have these solutions. Using a single objective genetic algorithm, we obtained this point. And by carefully compare this point and these solutions, we can see that there is some distance from the palette front in the case of weighted sum, but there is no distance between solutions and the palette front in the case of M approach. This means that if we compare this point and the one single solution from multi-objective approach solution is better than the single point. So in some cases, the M solutions have the better convergence than the single objective solution. This is because we can avoid the local solution thanks to the wide diversity of solutions. And now I'd like to explain some method in the second approach. First one is weighted sum. In the weighted sum, we use WeightVector. Two objectives are combined into a single objective function using WeightVector. Then this single objective is optimized by some method. In this case, optimal solution is here. Not this point, but this point is the optimal solution. This is okay. In this case, this is okay. However, if palette front shape is this one, somewhat concave around here, then solution is not around the center, but this point is the optimal solution. So final solution is this point. Decision maker is not happy. Decision maker want to have solution in the middle. So decision maker will change the weight vector slightly change this direction, then solution is here. So slight change in the weight vector can lead to a large jump in the case of weighted sum. And no solution around the center of the palette front can be found if the shape of the palette front is concave. These are two large problems in weighted sum up. To find solutions in concave region, we can use a constraint condition. When we have two objectives, one objective is still an objective function, but the other objective is handled as a constraint condition. So in this case, alpha is a parameter, and constraint condition is f1 should be larger than or equal to alpha. So the constraint condition says that this part is infeasible and this part is feasible solution. And under this constraint condition, we want to maximize f2. Then solution is here. So solution in the concave part can be found by this constraint condition method. However, this method has also some difficulties. One clear difficulty is by slightly changing the constraint condition, the result can be large jump. So slight change in the constraint condition can significantly improve or degrade the solutions. In this case, slight change in the constraint lead to a large improvement in F2 in this example. By changing from here to here, the objective value is largely improved from here to here. So this example shows that the result is sensitive to the specification of alpha value. And this may be not a good specification because slightly changing the value, we have much better solutions here. And another method is the use of target solution. And the objective is minimization of the distance from the target. So if we have a target here, we can obtain solution here. This looks nice because target can be directly specified. We want to this solution, but this is not the feasible solution. So the nearest feasible solution is found as a final solution. But this approach, this method is not so good because the specification of target is not so easy. If the target here, we have solutions here. But if we have target here, solutions here, by changing the target from here to here, the improvement of F1 is large and deterioration of F2 is very small. So slight decrease in F2 can significantly increase F1. That is significant improvement of F1. So if compared between these two solutions, usually we say that this is better because this is much better than this one for F1 and slightly worse than this one for F2. This is not a good specification. And if we know the shape of the palette front, we usually try to find solution around here, not around here. However, we have to specify the target using no information about the shape of the palette front. If we know the shape of the palette front, it's easy to specify a target. Okay, my target is here, and we want to find the solution around here. But we don't know the G shape. So without knowing G shape, we need to specify the target. This is the main difficulty. In the case of MO approach, many solutions are shown to the decision maker. A number of solutions are shown to the decision maker, and then decision maker can choose single solution, single final solution. But this is the advantage of MO approach. in a target solution-based approach, no information is available when the target is specified. So without knowing this shape, we need to specify this point. So in the first step, specification of the target solution without knowing the palette front shape. Then the second step is to find the nearest solution. And then this is the solution. And this solution is shown to the decision maker. Decision maker may be happy because the decision maker does not know the this shape. But in the MO approach, can show a large number of solutions. Then decision maker can choose a better solution. So the important issue in MO approach is how to search for well-distributed solution set along the palette front. Only when we have a well-distributed solution set, we can choose a good solution as a final solution. If the final solution set only here, we cannot choose this one because only this part is shown to the decision maker. So it is very important to find a well-distributed solution set. And the basic idea of MO algorithm is the same as the standard single objective algorithm. Simply iterate these 3 steps: evaluation and selection of good solutions and creation of new solutions. Simply iterate these steps. One difference is the use of specialized fitness evaluation mechanism in order to handle multi-objective environment. In the case of single objective, we can use that objective as an environment. But now we have multiple objectives. So we need a special fitness evaluation mechanism. In the case of single objective, it's easy to evaluate each solution, and it's easy to compare different solutions. If we have these 2 solutions, green and pink, if we need to compare these 2 solutions, it is easy to say that green solution is better than pink solution for maximization problem because we have only single objective. However, in the case of multi-objective optimization, it's not easy to evaluate the fitness of each solution. We need to specify, we need to assign a fitness value to each solution. What is the fitness of this solution? What is the fitness of this solution? We need to compare different solutions. Which is better between this one and this one? Based on the palette dominance, they are non-dominated. But in order to choose good solution, we need to compare these 2 solutions. The basic idea is the use of the palette dominance. This idea was suggested in Goldberg's well-known GA books. This one. And the idea is to assign high fitness to non-dominated solutions and low fitness to dominated solutions. In this example, high fitness values are assigned to these green solutions, and very low fitness values are assigned to these 2 red points, and medium fitness values are assigned to the other 3 solutions. Fitness assignment is to push the population towards this direction. The point is to push the population towards the palette front by assigning high fitness value to non-dominated solutions. So we can push the population towards palette front. However, if we simply use palette dominance relation, final population is around here, around the center of the palette front. It's very difficult to find solutions this region and this region. It is very difficult to increase the diversity of populations by simply using palette dominance. Thus, we need another mechanism. This is crowding. This idea has been used since the early 1990s. The idea is to assign high fitness value to isolated solutions and low fitness value to crowded solutions. In this example, all of these green solutions are non-dominated. So in the first palette dominance mechanism, all of them have high fitness values. However, in the second mechanism, these 2 isolated solutions have higher fitness values than these crowded solutions. So this mechanism is to increase the diversity or maintain the diversity. The second by using the second mechanism, we can increase the diversity in order to find the well-distributed solutions along the palette front. So now we have two different mechanisms: palette dominance to push the population towards the palette front, and crowding to increase the diversity. And the most important issue in MO algorithm design is how to maintain a good balance between these two mechanisms. By maintaining a good balance, we will obtain a well-distributed solutions along the palette front. However, this is a very simple mechanism, basic MO algorithm. So a lot of difficulties. One difficulty is convergence ability is not always strong. So we usually use elitist framework. In a basic framework, current populations here, and we select good solutions, and from good solution we generate new solutions. And new solutions are next population. And then we select good solutions and generate new solution. And new solutions are next population. It's very simple mechanism. However, this is not so good for convergence, because even when we have very good solution in the current population, this solution cannot survive to the next population. Next population is only children. So we usually use elitist framework. In the current well-known frequently used algorithm, all of them use elitist framework. Elitist framework is shown here. From current population, we generate offspring, children. And next population is selected from current population and offspring population. Not only from offspring, but also from current population. If we have a very good solution, then very good solution can survive next generation and can survive many generations, and good solution can be included in the final population. So the next population is selected from the current and offspring population. This is the elitist framework. And another difficulty is that solution distribution is not always good, simply based on crowding. So some algorithms use difference vectors. For example, in MOEAD, this is a well-known algorithm, and many other decomposition-based algorithms. Such directions are uniformly specified in the objective space. This is a result by NSG2. The NSG2 is based on a simple crowding distance. So solutions are obtained over the entire palette front, but distribution is not very good. Some solutions are very close to each other, and some regions have no solutions. By using such directions, uniformly distributed such direction, we can obtain well-distributed solution, as shown in this figure. This result is obtained by MOEAD. In MOEAD, we use uniformly distributed reference vectors. So search is performed along each reference vector. Then we have well-distributed final solution set. And another difficulty is convergence ability becomes very weak for many objective programs. So that this part, convergence, to push the palette front, this ability becomes very weak when we have many objectives. This is because under many objective situations, if we have, for example, 10 objectives, all of these solutions are non-dominated. So we cannot push the palette front towards the palette. We could not push the population towards the palette front using palette dominance relation. And there are many approaches have been proposed in order to handle many objective programs. And this is one of the current hot topic, evolutionary many objective optimization. In the field of evolutionary multi-objective optimization, multi-objective programs are further subdivided into two categories. One is multi-objective program. Usually, multi-objective program have 2 or 3 objectives. And the other category is many objective programs. When we have 4 objectives or more objectives, they often called many objective programs in the field of MO. When an optimization program has many objectives, for example, 10 objectives, almost all solutions in the current population are non-dominated. This means that we cannot use Pareto dominance relation as a solution evaluation criteria. And we have a huge number of good solutions because almost all solutions are non-dominated. For example, this figure shows the percentage of non-dominated solutions. This axis is the number of generations, and this axis is the percentage of non-dominant solutions among all the examined solutions. After 10,000 generations with 275 population size, we examine about 3 million solutions in the MO search. Among those about 3 million solutions, 85% solutions are non-dominated. That is, about 2 million solutions are non-dominated. We cannot say which is good solution, which is bad solution among those 2 million solutions. So this is the main difficulty of many objective optimization. And many objective optimizations is a very hot topic. As I have already shown the 5 recent award winner papers, 2 papers are on many objective optimization. And another hot topic is large-scale optimization. In many objective cases, we consider a large number of objectives. Now we consider huge number of decision variables. For example, 1,000 decision variables, 10,000 decision variables, 1 million decision variables. So the search is multi-objective search in a high-dimensional search space. Standard test program usually have 10 to 20 decision variables, and standard MO algorithms were designed for those test programs. So it's very difficult for standard MO algorithm to handle such a large-scale problem. Some special techniques are needed for efficient research to handle, large-scale multi and many objective optimization problems. This is one hot topic. And another one is expensive optimization. In some real-world applications, solution evaluation is very expensive or time-consuming. We need, for example, 1 hour to evaluate a single solution. We need to spend a huge amount of money to evaluate each solution. So we can examine only a small number of solutions in optimization. For example, we can evaluate only 500 solutions. If the population size is 100, we can update the current population only 5 times. It's not likely that we'll be able to find a good solution set after only 5 generations. So some special techniques are needed to handle such an expensive multi and many objective problem. One idea is use of surrogate-based optimization. The point is to approximate each objective function by a machine learning technique, for example, neural network, using a small number of examined solutions, and to apply an MO algorithm to a multi-objective problem with the approximated objectives. So the idea is to approximate each objective using a machine learning technique. Here, I show an example. This is an unknown true objective function. We don't know the shape of this function, and we can examine only a small number of solutions. Then we use some machine learning technique to approximate the original function. So we assume that this red line is an approximation result. This approximation result is not the same as a true function, and approximation quality is not so very good, but we can find some region, some promising region. Then we evaluate some new solutions. After evaluating some new solutions, we can apply the same machine learning technique using this new point and old point. Then we may have a better approximation. Then we will be able to find good solutions. This is the idea of surrogate-based optimization. And another topic is weight vector adaptation in MOED. As I have already explained, very good result can be obtained by using uniformly distributed weight vectors. So using uniformly distributed weight vector, we can obtain very nice solution set. However, if palette front is not this shape, for example, inverted shape is not consistent with weight vector distribution shape. So the final result is not very good. Not uniformly distributed solutions. Because weight vector distribution is this triangle. And palette front is this shape. So no solutions are obtained here and here and here. And many solutions are obtained here because these solutions are for weight vectors in this region. And these solutions are solutions for weight vector in this region. Thus, weight vector adaptation is needed in order to find some special shape of palette front. For example, this shape, this is a palette front of WFG3, very special shape. And weight vector distribution is this one. So it is very easy to say that, oh, this weight vector distribution is not good for this shape. And actually, using this weight vector, uniformly distributed weight vector, we obtain these solutions. And red point are obtained from this red point. And all the other weight vector generate solutions on this line. And only one point is obtained here. No solutions around here. So this result also shows the necessity of weight vector adaptation in MOEAD. And another topic is constraint, multi and many objective optimization. Almost all MO algorithms have been developed for multi-objective optimization problem with no constraint condition. However, in real-world application, we usually have constraint conditions. So it is important to handle constraint conditions, constraint multi-objective optimization problems. And an interesting idea is how to utilize infeasible solutions for efficient search. So here, this figure shows the true palette front is here, but if we remove constraint conditions, palette front is here, unconstrained palette front is here. So if we ignore constraint condition, we have solution on around here, C region. But our goal is to find a solution in this yellow region. The idea is to efficiently utilize solution in C and also solution in B. These are infeasible solutions in order to efficiently pull solutions in A. And another topic is multimodal optimization. This is a special type of optimization problems. The problem definition is here. Each point on the palette front, correspond to different palette optimal solutions in the decision space. In objective space, we have only a single point, but this point is related to different solutions. Different solutions have almost the same objective values. And the goal is to find well-distributed solutions on the palette front and also find these two different solutions. This is a multimodal optimization. And another topic is utilization of stored solutions in unbounded archive. This part is a current multi-objective optimization framework, elitist framework, current population and offspring population, and next population. We can store all the examined solutions. Currently, memory is not so expensive, so it's not difficult to store all the examined solutions. And one idea is to utilize examined solutions, stored examined solution in the main MO part. So how to utilize the stored solutions for the search in the main MO part? This is the one research direction. Another research direction is how to choose the final solution set from all the examined solutions. So in this framework, the final result is not the final population. We try to obtain better final solution set by selecting from all the examined solutions. This is another research topic. As we have already explained, we can find 2 million solutions. So it's not so easy to select, for example, 100 solutions from 2 million solutions. So this is a very interesting research topic. And another topic is preference incorporation during the MO search. The original version of MO algorithm is to try to find all the palette optimal solutions, well-distributed solutions along the entire palette front. However, if some information is available from the decision maker, we can bias the search toward some region, preferred region by decision maker. If we can do this, this may be more efficient than try to find all solutions along this palette front. We can focus on some region if preference information is available from the decision maker. This is one hot topic. And of course, we have various applications of MO algorithms, as shown by this number of multi-objective papers. Last year, we have about 5,000 papers with multi-objective in paper title. I think that most of them are application papers. Now, I'd like to move to the final very short chapter. Other useful information on MO. We have specialized conference, MO conference, international conference on evolutionary multi-criteria optimization. This is only for MO papers. First conference was in 2001 in Switzerland, and second conference in 2003. Every 2 years, we have this conference. And 3 years ago, the conference was in Michigan State University, organized by Korean Dev. And last year, we had this conference in Shenzhen. And next year, the conference will be in Leiden in Netherlands. And in other conferences, we have MO tracks and some related tutorials, for example, in Gecko. In CC, we have some related special sessions and tutorials. In SSCI conference, this year, it will be in Singapore. And we have MCDM Symposium. MCDM Symposium can include MO papers. And we usually have many MO papers in PPSN conference. And currently, many MO algorithms and many test programs are available through the internet. These three are well-known sites for MO researchers. One is JMetal. JMetal is mainly for Java users. The paper title is here, JMetal, a Java framework for multi-objective optimization. You can easily find this site using, for example, Google search. And this paper was published about 10 years ago. And then ProtEmo. ProtEmo is for MATLAB users by Chinese researchers. This site is by European researchers. And ProtEmo, a MATLAB platform for evolutionary multi-objective optimization. Then for Python users, we have PyMo. This site is organized by Michigan State University, Korean Dev, and his group members. So you can easily find, and you can easily use MO algorithm, and you can easily evaluate your algorithm using test programs. And now I'd like to conclude my presentation. First conclusion is here. Evolutionary multi-objective optimization, MO, is a rapidly growing research field, as shown by this figure, with a number of interesting research topics, as I have already explained as hot topics. Since this field is still a young research field, and MO has a wide variety of application areas, since almost all optimization programs have conflicting objectives. I show some references. First one is a very easy paper written for magazine. How to compare MO algorithm using test program and performance indicators. Second paper is for a new MO algorithm framework with unbounded external archive. Third one and fourth one is on subset selection from a huge number of candidate solutions for standard multi-objective optimization and for multimodal multi-objective optimization. Last one is for large-scale optimization. All for today. Thank you very much. Any questions are welcome about not only MO algorithm, but also on IEEE CIS, IEEE CIS journal, CIS conference, SSCI this year in Singapore. I'm a program chair for this conference. And WCCI 2024, this will be in Japan. I'm a general chair and about my research group in China. I always welcome highly motivated young researchers in my research group. Thank you very much.
Hi. Do you guys have any questions to Prof. Hisao? If you have questions, please, put it on the chat or probably raise your hand using the feature. All right, everyone seems to be pretty shy then. Questions? No? Then maybe I will just ask a question. Because I'm also I have no idea about multi-objective optimization. So I think on the page slides number 92, it's about these dominance, the steps number 1 where you push your Pareto dominance and crowding. So you are saying that in the crowding, you are looking onto high fitness, low fitness, right? To actually try to diversify the solution.
Yes, yep.
But at the Pareto front, most of the shape of it is actually very close to each other as well, right?
Yes.
I mean, yeah. So how does it work? Because you're trying to diversify the solution, but at the same time, the Pareto front actually is also very close to each other.
Yes, you're right. Yes. So usually all of them have very similar fitness. Only this one,
Mm.
the extreme one, has much higher fitness value. And the other side, only extreme one has a very high fitness value. So in the case of two objectives, when the result is something like this, if current population is something like this, only two extreme points have large fitness values. So we can gradually increase the diversity. And in this case, this part, when the current population is something like this yellow part, for example, this part has a large fitness. But finally, if we have a very nice distribution and each solutions are very close to each other, only two extreme solutions, extreme solutions have high fitness values. And those two extreme solutions contribute to gradually increase the diversity.
Okay.
Still, we need to further improve the diversity because this part is not covered. This result is not perfect after 2000 generation update.
Mm.
And if we continue to do this search, thanks to high fitness value of the end extreme 2 point, we can gradually increase, but not so very fast.
Oh, okay. All right. So this fitness value is evaluated based on the neighborhood solutions or based on like all the solutions?
So the best, in this case, this special algorithm is based on neighborhood solutions.
All right. Okay.
For efficient calculation.
Okay. Sure. I think there is a question from Dr. Ahmed. He was asking, what's your opinion with inventing so many algorithms that is based on the same mathematical basis, but take different names and claim novelty?
Oh, this is a very interesting questions. I think that there are two levels. One level is in evolutionary multi-objective field. A large number of similar but slightly different algorithms have been proposed. And then those algorithms are submitted to journals at conference. Some of them are accepted, some of them are rejected. But eventually, they try to submit different journals. If that paper is rejected, then eventually those papers have been also published. But that's not so very bad because evolutionary computation itself is based on gradual improvement. So the accumulation of such a gradual improvement may lead to good algorithm. This is one view. And another level is some researchers use totally different names based on very similar mechanism. Those names is, for example, of gray wolf algorithm, ant-lion algorithms, whale algorithms, or many others using some name of insect or using of some animals. Basically, those algorithms are very similar. Those of them are population-based algorithms. Difference is very small. And personally, I don't like such trend. But the researcher want to publish papers and want to attract much attention using some attractive name. So I noticed that such a trend, they try to use many different names from some names, the animal names or insect names. So I'm not very sure, but personally, I don't like that trend. But within some research field, gradual improvement, I think that it's okay, and it's important. That's my opinion. Thank you very much for such an interesting question.
Okay, is there any other question from the floor? Okay, I guess there's no much question on this. I think it's a newly explored field, and if you have any questions that you need to ask, there is a question. There is a question. Sorry. From Dr. Saleh. In evolutionary algorithms, if we increase the random solutions or random factors, does that improve the optimal solution or accepted as an improvement?
Well, thank you very much. If I think the increase the random solution means that we use larger population size. I assume that the question means that if we use larger population size, what's happened? If the total number of evaluated solution is the same, then I think that there is some optimal specification about the population size. But if the total number of generation is the same, larger population will lead to better solutions. So in general, population size is large. We will be able to obtain better solutions. But by increasing the population size, we need more computation resource. That's question. Is that the answer to your question?
Yeah.
I'm not sure this answer is good answer to that question or not.
Oh, hi, Dr. Saleh. Okay. All right. So Dr. Christopher is asking, we have high dimensionality of objectives at the parietal fronts. Is there any benefit in reducing the dimensionality of the objective so as to still have a representative parietal front for the EMO approach?
Yes, yes. I agree. Yes, my answer is yes. There are several research on dimensionality deduction. This is because if we have, for example, 10 objectives, some objectives are closely related to each other, especially in real-world application. When I talk with Korean dev, when Korean dev worked with some automobile company and do some optimization of design, he told me that originally he had more than 20 objectives. But after careful examination, those 20 objectives reduced to several objectives. So it is important to decrease the number of objectives before solving many objective problems. If all objectives are independent with no close correlations, it's very difficult to remove some objective. So in that case, we need to solve the original many objective problem as many objective problem. Then we have huge number of non-dominated solutions. But in general, my answer is yes, it's important to try to decrease some closely related objectives. So, and the dimensionality deduction in many objective optimization is one research direction. Thank you very much.
Does that answer your question, Dr. Christopher? Right. Okay. So any other questions
Yes, thank
are
you.
welcome. All right. Thank you so much. Okay, Mr. Dr. Saleh was asking on the mechanism of creating initial new factors to discover the domain.
Oh. So I think that this question is related to adaptation of weight vectors.
Hi, Dr. Saleh. You probably wants to clarify. Maybe you can turn on your mic and then probably has a more explain your questions to Prof. Hisao so that you can get specific answers that you want. Hi, Dr. Saleh.
Yes. Do you hear me?
Yeah, I can hear you clear.
Actually, I am doing PhD about evolutionary logarithms. So I am working on new mechanism in, to generate vectors, initial vectors, and so does that improve the evolutionary logarithms, or what the Prof said about that? So I'm concerned about this idea. If he
Okay, so the initial new vectors mean the initial solutions?
yes, initial solution, yes.
Okay. Well, that's a very interesting, and it's very important. Actually, it's important. So in evolutionary computation in general, we usually randomly generate initial solutions, but this is not so efficient. In order to evaluate different algorithms, we use the same condition. So usually we use randomly generated initial solution, but in real world application, it's not good. So it's for real world application, it's very important to create good initial solutions. But the question is how to generate good initial solutions. It may depend on application field. Each application field have some heuristics, some optimization algorithm in each application field. So we can use some heuristic method or greedy method in order to generate new initial solutions. Those solutions may be much better than randomly generated solutions. In general, that's a very important issue and very useful in real-world application. However, in algorithm development, many researchers are solving test programs. Those test programs are usually very easy, and there are no heuristics, no greedy algorithm. So we usually use randomly generated initial solution. But if we focus on some special applications, we may need good initialization methods in order to find good initial solutions. Thank you very much.
Thank you, sir. Thank you so much.
Okay, I hope that answer your doubts. Any other questions for Prof. Hisao? Okay, I think that's about it, Prof. Hisao. So if you are shy, all right, you know.
I'm very shy.
So if you are shy, but still you actually have a lot of curiosity about this multi-objective optimization, I've actually put down the email of Prof. Hisao for you to actually send email to him, have a close Q&A session with him. All right, and on the chat, and if you have any information or any questions on the IEEE CIS Malaysia, I've also put down the contacts for our chair in Malaysia. So anything you can just email the both of them. Can you get the recording? I think it's I'm going to submit this recorded video to the IEEE CIS as well. So I think it's open. It's open for everyone to this. You probably can just send me an email. I think I send you the invitation. So you send me an email if you are interested in the recording, and I probably share it with you.
Oh, I can. If someone want to have this slide, I can send the slide based on the email request.
Okay, sure. So if you want Prof. Hisao slides, you can just send him an email for this. Yep, sure, Christopher. So I think you send email to Prof. Hisao, Dr. Christopher, and he will send it to you. So I think it's more on the personal one-to-one based on the request.
Yes.
Is that right?
Yes.
Okay. Okay. Thank you so much. And all right. Okay. So I think I will end this talk, and thank you so much for your presentation and for your talk. It was a very good and informative on the multi-objective optimization.
Okay. Thank you very much.
Yep. All right. Okay.
Thank you so much
I think.
for great presentation.
All right. Hopefully you guys have a nice day, and thank you so much.
Thank you.
All
Thank
right.
you.
Okay.
Bye-bye.
Bye.
Bye.